In this video, we're going to be going over one of our discrete probability distributions called the binomial distribution. And before we get into what the binomial distribution actually looks like, we're first going to cover 5 different characteristics of the binomial distribution. The first characteristic is that the experiment consists of n identical trials. So our first characteristic is n identical trials. The second characteristic is that there are only 2 possible outcomes for each trial, and we will denote one outcome as an S for a success and the other as an F for a failure. So 2 is 2 possible outcomes. And we have S for success and F for failure. Number 3 is the probability of a success remains the same from trial to trial. And this probability is denoted by P, and the probability of F is denoted by Q, which is just 1 minus P. So number 3 is that the probability of a success is equal to P, and the probability of a failure is equal to 1 minus P, which is equal to Q. Our fourth characteristic is that trials are independent. Meaning that if we have a success in one trial, it doesn't affect the next trial, or if we have a failure in that same trial, it doesn't affect that following trial. And finally, number 5 is the binomial random variable, x, is then just the number of successes that we have in n trials. So x is the number of s's in n trials. So now that we have the basic characteristics for our binomial probability distribution, let's look at what that distribution actually looks like. So the probability distribution is P of x. So the probability of x number of successes in n trials is equal to the number of trials that we're conducting, so n, choose x, so we have our choose function from a previous video, multiplied by the probability of a success, so P, raised to the number of successes that we have, so raised to the x, times the probability of a failure, or Q, raised to the number of trials minus the number of successes, so the number of failures that we have, so it's just n minus x, and that's going to be our probability distribution. And we can do that for x is equal to 0, 1, 2, all the way up to n. And to break down what each of these different values are again, we have P is our probability of a success. Q is our probability of a failure, which is just equal to 1 minus P. We have N, which are our number of trials. We have X, which are our number of successes in those n trials. We have n minus x, which is our number of failures. And then just to quickly review what our choose function is. So our choose function was n choose x, which is just going to be equal to n factorial divided by x factorial times n minus x factorial. So that's our choose function from before. So if we walk through this quickly one more time, we have our probability of getting x number of successes in our n trials is equal to n, the number of trials we have, choose x, so choose the number of successes, multiplied by the probability of a success, raised to the number of successes, times the probability of a failure, raised to the number of failures that we're having in our example. In a previous video, we walked through how to calculate both the mean and the variance for any discrete probability distribution. So let's just quickly review those. So we had our mean, which was mu, or we could write it as the expected value of x, which is equal to the sum of each of our x's, so x, times the probability of occurrence, so times P of x. And that's going to give us our expected value or our mean of that distribution. We could also calculate the variance, which was sigma squared, or the expected value of our x minus mu squared. And if we write that out as a sum, we get the sum of x minus mu, that quantity squared, times the probability of x happening. So times p of x. So we can use both of these formulas to calculate both the mean and the variance for any discrete distribution that we have. And then remember, we can just calculate the standard deviation as the square root of sigma squared, which is just sigma is equal to the square root of our giant sum. So the sum of x minus mu squared times p of x. However, this is assuming we don't really know anything about our discrete distribution. Since we know that we're dealing with a binomial distribution for this example, we actually have some really nice shortcuts for calculating all these values. So for our mean, it's still going to be mu. It's still going to be the expected value of x. So instead of walking through our formula for all the different possibilities for x times our probability of occurrence, we can just say that this is equal to n, or the number of trials that we're conducting, times p, which is our probability of success, and that's going to give us our expected number of successes in our n trials. So the mean is just simply calculated as n times p when we're dealing with a binomial distribution. We have a similar formula for the variance, so we can say the variance, which is again our sigma squared, is equal to our expected value of x minus mu squared, which is now just equal to n times p times our probability of failure, or q. So our variance is now just npq, and our mean is np if we're dealing with a binomial distribution. And again, our standard deviation, which is our sigma, is just equal to the square root of npq. So we have some really nice shortcuts when we're dealing with our binomial distribution for calculating the mean, the variance, and the standard deviation. So now that we have all the basics down for our binomial distribution, let's just walk through a quick example. So for our example, we're going to be conducting 3 trials. So we're going to say n is equal to 3. In each of those trials, we're just going to be flipping a coin, and that coin is going to be weighted. So the probability of a success, which we're going to call getting ahead, is 1 out of 4. So probability of flipping heads is 1/4. So that means q is equal to 1 minus p is equal to 3 out of 4. So the probability of getting a tail is 3/4. Probability of getting the heads is 1/4. So now let's say we want to calculate the probability of getting 2 heads in our 3 coin flips. So that would be the probability that x, or our number of successes, is equal to 2, given that our number of trials, or n, is equal to 3. So if we fill in our formula, we get n choose x, so we have 3 choose 2, times the probability of a success, so 1/4, raised to the number of successes that we have, so 2, times the probability of a failure, which is 3 out of 4, so 3/4, raised to the number of failures that we're observing, so 3 minus 2 is just 1. Then we can just walk through our formula and calculate out all these values. So our 3 choose 2 is 3 factorial over 2 factorial times 3 minus 2, or 1 factorial, times 1/4 squared, which is just 1/16, times 3/4 to the first, which is 3/4. We fill in these values, we get 3 times 2 times 1, or 3 times 2 factorial, divided by 2 factorial. So we're just going to get 3 times 1/16 times 3/4, which is going to be equal to 9/64, or approximately 0.14. So that's our probability of getting 2 successes in 3 trials when the probability of success is 1/4. But what would be our actual expected number of successes from this experiment? So remember, our mean, mu, is just going to be equal to n times p, so n times the probability of success. So we have n is equal to 3, p is 1/4, so 3 times 1/4 is just going to be equal to 3/4. So our expected number of successes in 3 trials is 3/4 of a success. So remember, This value doesn't need to be a whole number, doesn't need to sum to 1. It's just going to be our expected number or our average number of successes in 3 trials if we run this experiment an infinite number of times. Let's also quickly calculate the variance for that. So we have sigma squared is just equal to n times p times q, which is 3 times 1 over 4 times 3 over 4, which is just going to be equal to 3 times 3 on the top over 4 times 4 on the bottom, so 9 over 16. So our variance for our binomial distribution is 9/16 with a mean of 3/4. And now just to give you a quick note about how the probability for this is going to work. If we want to find for a range of values, say if we wanted to find the probability that x is greater than or equal to 2, we would have to find the probability that x is equal to 2 and the probability that x is equal to 3, and we would just add those together. So x is equal to 3, and we would add those together to get the probability that x is greater than or equal to 2. And the same would happen for any inequality that we have here. So x is greater than some value, x is less than some value, x is greater than or equal to some value. We need to walk through for each of the different values that x is going to be equal to that are relevant to our equation and fill in those values and add them all together to get the probability of that actually occurring.